All right, welcome back everybody to the Data Voice and Video Cabling, Chapter 2, the Technology of Communications. Now, what we're hoping to get out of this chapter is that you'll be able to understand the basic operations of telephone, uh, video transmission, cable TV networks, and computer networks. We'll be covering three primary communication technologies, voice, video, and data. Now, first, we'll cover basic telephone technologies and telephone networks, which, aside from telegraphy, um, were the first communication technologies and which provided that technical base for succeeding technologies. Next, we will cover television and video systems, obviously one of our most important technologies. And finally, we'll cover computer networks, the importance of which is hard to overestimate. And as we begin this section, we're going to cover just the basics of these technologies. We'll then progress to the cabling technologies, first covering copper wire, and then fiber optics, with complete explanations of their operation and the installations. So let's begin with the operations of the telephones themselves. Now, the modern telephones operate on essentially the same principles that they were developed over 100 years ago. They still use a single pair of wires that connect the phones and a power source. Now, when the phones are connected, the power source causes a current to flow in a loop, which is modulated by the voice signal from the transmitter in one handset and then excites the receiver in the opposite handset. Dialing was originally done by a rotary dial, which that simply switched the current on and off in a number of pulses corresponding to the number dialed. Dialing is now mostly, but not entirely, accomplished with tones. By operating on a current loop, phones can be powered from a central source and extended simply by adding more wire and phones in parallel. Most phones are now electronic, that is, they use semiconductors rather than electromechanical devices. But they use the same type of wiring, frequently called current loop wiring. In office systems, the phones are sometimes digital and they use twisted pair wiring in a manner similar to computer networks, but at much lower speeds. Telephone wiring is simple because the bandwidth of a telephone signal is low, generally around 3000 hertz or 3000 cycles per second. Bandwidth is similar to speed. A low bandwidth requires lower frequencies and a higher bandwidth requires higher frequencies. Computer modems use sophisticated modulation techniques to send much faster digital signals over low bandwidth phone connections. And many telephone networks offer a higher speed version of the modem called Digital Subscriber Line, or DSL, which provides a high speed internet connection to the home. Now, DSL has many varieties that offer various connection speeds, but common to all is the dependence of speed on distance to the subscriber, limiting higher speeds to those close to the central office. And because of the low bandwidth and current loop transmission, telephone wire is easy to install and test. It can be pulled without fear, and if it is continuous, it should work. Now, outside the home or office, the phone connects into a worldwide network of telephones, all connected together by a combination of copper wire and fiber optic cables, leading to switches that can interconnect any two phones for a voice conversation or data transmission. These switches create a switched star network where each switch knows how to find every phone by connecting through successive switches. When a phone connection is made, the connection stays complete as long as the user or users require creating a continual virtual pathway between the two phones. Telephone cabling can be a simple four-wire cables inside the home, but four-pair unshielded twisted pair cable are typically used inside an office and are now required by the FCC regulations inside the home. The subscriber loop connections to local switches have been on multi-pair wires with up to 4,200 pairs per cable. Most of these large pair count cables have been replaced by fiber optics because Those 4,200 pairs of copper wires can be replaced easily by a pair of single-mode optical fibers. All fibers used in telephone networks are single-mode types. Telephone connections between local switches and inter-office trunks are predominantly optical fiber ready, and soon will be all fiber. Long distance has been virtually all fiber for years, except in areas of exceedingly rugged terrain or isolation where terrestrial radio or satellite links are more cost effective. Even fiber optic undersea links have overtaken satellites for international calls because of the higher capacity and lower cost of fiber compared to satellites. Now, the next stage of deployment of optical fiber in the telephone network is fiber to the home, or FTTH. Now, while it will take many years to convert all home connections from copper to fiber optics, phone companies, municipalities, and private companies are converting subscribers to fiber at a rate of millions of homes, apartments, and condominiums a year. The higher bandwidth of fiber to the home will usher in new residential services that will more than pay for the fiber, but savings in maintenance over aging copper plants may be sufficient justification in many regions. Another technical development affecting the telephone business is voice over IP, or voice over internet protocol, VoIP. This uses a private or internet connection to transport digital voice and connect it into the normal phone system where necessary. VoIP is now widely used by businesses and consumers who are willing to trade some quality of service for a lower cost. Now, as network speeds and capacities increase, VoIP quality of service has improved to acceptable levels, increasing its market acceptance. VoIP uses standard cabling infrastructure with new phone hardware, which brings us to the video transmission. Now, probably the easiest way to explain basic video or TV technology is to use the fax machine as an example. Fax machines could be called slow scan television. They send one picture frame at a time in black and white over telephone lines. We're all familiar with the process. The machine scans one line at a time, interprets that area as black or white space, translates the information into electronic pulses, and then transfers the information to a receiver. Now, black and white television uses the same technology as a fax machine, except at 60 frames per second, and using a camera rather than a scanner. And each line of the image is scanned and translated into a complex video signal. The color TV process is the same, except it has a still more complex signal being used. And because of the complexity of the television signal, it requires a lot of bandwidth. A standard TV channel uses 6 megahertz, or 6 million cycles per second of bandwidth. Now, in other words, the signal requires 6 million cycles per second, each cycle contributing part of the signal information. To get all the information sent fast enough, we could send video signals at lower speeds, but the images would then be in slow motion. Now, we have closed circuit TV, or CCTV, used for surveillance and security systems, consists of only one channel operating with a direct cable connection to a monitor. In a large system, video switches scan numerous cameras to allow the monitoring of many local or locations, but each remote camera is connected to the central monitor by an individual cable. In order for these multiple channels, each channel must use separate frequencies, or else their signals would be jumbled together. For example, the FCC is assigned channel 2 the frequency range of 54 to 60 megahertz. Channel 3 has 60 to 66 megahertz. Channel 4 has 66 to 72 megahertz, and so on. The UHF channels go up to 890 megahertz. Each channel transmits its programming in that 6 megahertz channel. A broadcast TV sends its signals over the air by modulating a signal on a transmitting antenna that is received by a smaller antenna on your home or TV. Cable TV works the same way, except it is sending the signal through coaxial copper cable or optical fiber, not via radio waves. One of the very intimidating words used in the TV business is modulation. Now, modulation is simply the function of taking a basic 6 MHz TV signal and modifying it so that it matches one of the standard channel frequencies. For example, the TV signal coming out of the camera at your local station operates at about 6 MHz. If we assume that your station is channel 13, it must send its programs in the 210 to 216 MHz slot. So before sending the signal to the antenna, it must change the 6 MHz signal to a 210 to 216 MHz signal. Now the conversion is done with a special electronic device called a modulator. Your VCR has a modulator built into it, because videotape cannot record the very high frequencies used in broadcasting. So in the previous example, the station used a 216 MHz. The VCR must record at frequencies that are too low for a television tuner to pick up. So when you play a videotape, the information from the tape is modulated to channel 3 or 4, which your TV can then display. Once we begin to customize television systems in the home or office, the modulator becomes a very important device. It's necessary to assume or to assign the various video inputs to specific channels so that a television can use them correctly. Video distribution systems allow for custom television channels to be transmitted through the facility. It's generally done in combination with a cable TV system, although these systems are capable of handling well over 100 stations. Very few use them all. Now this allows the owner to transmit other signals through the unused channels. Channels are assigned with the use of a modulator which applies the basic television signal to any channel. Sending the signal requires much more bandwidth than that required by telephones. So when the technology was first developed, the only cable capable of carrying these high-speed signals with adequately low loss was coax cable, also called coaxial cable. Now it uses a central conductor surrounded by an insulator. Then the outer conductor, or conductive webbing, called the shield, and then finally a plastic jacket. It's the design of the cable with the central conductor widely and evenly separated from the outer conductor that gives it the high bandwidth capability. In addition, the outer conductor acts to contain the signal inside the cable, reducing the emissions from the cable that cause interference in other electronics and the interference of other outside sources on the signal in the cable itself. The signal in coax cable is a simple voltage. It can be introduced into the cable at either end or even in the middle, where it will be carried by either end. In any application, it's important that the transmitters be selected to be appropriate to the characteristics of the coax cable. And both ends must be terminated to prevent reflections that could then cause interference. Coax must be installed with care. It should not be stretched or kinked. Doing so will reduce the level of bandwidth it will transmit. Connectors should be carefully installed to prevent what we call signal leakage, which is the TV term analogous for signal loss. And unused ends must be properly terminated to prevent reflections, or what we call signal bounce back. The cable TV networks are set up in a particular way. Televisions delivered by broadcasting are simply delivering the same signal to all directions and users at one time. It may be delivered by terrestrial antenna or to a home televisions, sent to satellites that rebroadcast it to large geographic areas at once, or transmitted by coax cable on a CATV system. Most CATV systems get their broadcast signals from satellites at a location called the head end, which then sends it out over large low-loss coaxial cable called an RG8. The RG standing for radio gauge, about an inch in diameter. These cables terminate in amplifiers that rebroadcast it over many other cables to more amplifiers, which repeat in the rebroadcast. Thus, the CATV system looks like a tree in a branch system, the name used to describe the network architecture. The obvious fault of this type of system is its vulnerability to the failure of a signal amplifier. If any amplifier fails, service is lost to all the downstream customers, The solution then would be to separate the network into smaller segments to prevent massive failures. Today, most cable TV or CATV system operators have switched over to a hybrid fiber coax or HFC with fiber optic cable distributing head-end signals to local drop amplifiers for distribution to the homes. By using fiber for the head-end connection, the number of amplifiers connected in series is reduced to about 4, minimizing the number of drops affected by a single amplifier or cable fault. This greatly enhances system reliability and minimizes maintenance costs. Fiber is added to the CATV systems already in place by a fiber overbuild, where a fiber optic cable is lashed to aerial coax or pulled alongside in its ducts. Large systems use fiber to distribute signals to several towns because fiber has the capability of transmitting long distances, saving on the cost of additional head ends. Once a CATV signal is split off to the house, it's carried on a smaller coax cable to and throughout the home to connect all the TVs. This cable, although smaller, can still carry gigahertz bandwidth signals necessary for transmission of up to 100 or more channels of video programming. The next step in television is digital TV. Now, it has been mandated by the FCC, but the implementation date has been shifted several times. By converting the digital TV broadcast spectrum, it'll be opened up for other services. However, older analog TVs will need converters or will need to be replaced. Further development is using the internet for delivery of video services, including TV. Internet Protocol TV, IPTV, will allow more competition in TV markets and the delivery of many more channels. These developments underscore the importance of developing high bandwidth cabling infrastructure to transport these services. Now, next on our slate here will be cable or computer networks. Now, there is no computing trend in recent years that has been as large or as important as networking. The use of networking has risen steadily in the past 10 years and is continuing to spread throughout the marketplace. There are so many different types of networks available, so many variations of connections, variations of signals, and so on that the entire subject can be very confusing. Our coverage of networking will proceed slowly and carefully, covering and explaining all the various parts. The purpose of networking is to allow a number of computers to operate together, sharing information and allowing the operator of one computer to read and use programs in another computer. Networking is an important technology in offices. For instance, bookkeepers do all their work on computers in their offices, but unless their computers are somehow connected to their company's computers through a network, the others have no way of obtaining financial information from their own company unless the bookkeepers bring them reports. Neither can anyone else in the company get pertinent financial information from the bookkeeping system without a special effort. The same goes for any type of order processing system, sales reports, analysis reports, or whatever information and data a business may use. With a network, however, all this information, except information that is specifically excluded, such as confidential and financial data, is available to whoever needs it, whenever they need it. The confusing part of networking comes when we devise methods for connecting these computers together and give new names to various parts that are used to connect them. The following are the fundamental parts of networks. 1. Digital computers. Phones and TVs are basically analog transmission networks. They began as electrical signals of continuously varying voltages or currents traveling over the cables. Computers, however, are digital. Computer data is represented by ones and zeros, and that can be stored and manipulated by digital processing. Computer programs express all data, graphics, and programs as digital data. Analog signals are subject to distortion and degradation by noise and attenuation. Digital signals are immune to noise and tolerate greater attenuation, simply because the receiver only needs to distinguish between a 1 and a 0, not a continuously varying signal. And besides computers, most phone signals are digitized as soon as they reach the phone company central office. This not only allows for better signal quality over long distances, but allows for the multiplexing or compressing of digital data into high bandwidth digital signals carrying numerous phone calls. Digital television is also in the near future for similar reasons. If the network is going to allow personal computers to communicate, each computer must have some way of getting into it. So for wired networks, this is done through the use of an Ethernet data port in the computer or a network interface card or NIC. The NIC is a circuit card that fits into one of the expansion slots in the back of a personal computer that provides a data port. This is the most vital link between the processor and the network. It interprets information between the computer and the network and feeds information in and out of the computer in a way that both the computer and the network can accept. Wireless connections between the computer and the network are made using high-frequency radio links, with data processed to maximize data transfer over limited bandwidth. PC laptops generally have wireless connections built in, while desktop computers may require a separate wireless card. Network architecture and protocol. Now, how are the computers linked and what language do they use to communicate? Is one of the processors or computers the base of the network and hence the most important, or all the processors connected to the network considered and treated equally? Most networks use one computer, usually the most powerful, as the heart of the network, and other computers on the network use it as the main source of data storage and retrieval. The central computer is generally called the server or file server, and the satellite computers are commonly called clients and nodes. If all computers on a network are equal and share data amongst themselves, the network is called a peer-to-peer network. And most networks are client-server networks, where a central computer, the server, acts as the main depository of all the files that may be shared by all users, the clients. Now, when we're discussing the file servers being the center of most networks, it is important to talk about what types of computers these servers are. Now, typically, when the word server is used, it refers to a high-quality personal computer or workstation, usually a new state-of-the-art unit. When, however, you hear the word host, this refers to a mainframe or a mini computer being used as the center of the network. Now, host computers are usually used in large networks at large companies, and these companies frequently have large centralized operations that require huge amounts of storage and processing capabilities that are available only in mainframe computers. Now, for these companies, it simply makes sense to connect their networks to this central information source that is already running most of their company's operations. Small companies with their different needs rarely require a mainframe computer. They nearly always use file servers rather than host computers or peer-to-peer networks. Now, just as computers have an operating system that controls all of its hardware and allows applications software to run the computer, networks have operating systems that control the flow of information on the network. The network operating system establishes what computers are on a network, what peripherals they share, and how data is formed for transfer. It even detects and corrects errors in data caused during transmission. Now, because networks send various routing commands through their systems, software that is not written for networks, where it will be exposed to these strange commands, often will not work properly. Many of the more popular types of software come in network version. It's very important to verify that your software is compatible to your network before you install it. Copyright laws may also limit the use of software on networks, depending on the license agreements from these manufacturers. Network protocols are the language that your computers use to communicate and speak. It specifies how the data is encoded for transmission, how addresses are specified, and how access to the network is gained. Each network is different in these aspects, requiring what we call bridges to translate protocols to allow different networks to communicate. Topology is the connection pattern of computers in the network. There are several methods for connecting all the computers of a network together, and some of the most common methods are the star topology, where all computers are attached to a central computer or a central hub. The ring, where all computers are connected in a series along a ring, and the bus, all computers are connected to a single cable. The bus topology looks like all the computers are connected to one central cable. This is how it was actually done with the first Ethernet networks. The cable was a thick, stiff coaxial cable, and the computer was connected directly to the cable by cutting a hole in the cable with a coring tool and then attaching a network transceiver. Ethernet cable was expensive and difficult to install, but necessary to provide the performance needed for reliable transmission. Later networks used thin coax cable and with twist lock connectors, which was less expensive and easier to install. In the ring topology, the computers are simply connected together in a large ring. It's done by either optical fiber, twisted pair, or coax. But the most popular legacy ring networks, Token Ring, used a shielded two-pair cable, and fiber distributed data interface used fiber optics, or FDDI. Note that in this arrangement, each computer has two cables connecting to it, one from the previous computer in line, and one for the next computer in line. A star topology is an arrangement where all computers on the network connect to a central point. This connecting point can be the file server or main computer, or it may be a hub or a switch. Hubs act as communication points, taking signals from all the connected computers and then broadcasting them to all other computers connected to the hub, and then multiplexing the signals to communicate to other computers or hubs over the backbone or main wire. Switches are similar to hubs, but they do not broadcast inputs. Instead, they switch them to their destinations based on the addresses provided by the sending computer. This is why hubs are not considered obsolete. From this central computer or hub, there are a number of cable runs to the various satellite stations or nodes. We call these home runs. In actual practice, each computer has only one cable connected to it, with all these cables feeding from the one central location, where the file server or the hub or switch would be located. So which network topology you use is determined by the type of network you plan to install. Some require one type of connection and some require others. There can be advantages and disadvantages to all types. Networks have evolved, however, to a common star wiring scheme or cabling architecture, no matter what the network topology, to accommodate all the topologies. Now, once you have a network interface in place, you need some method of getting the data signals from one computer to another. It can be done by a number of different ways, although one of the following methods can be used. The first in the list, the twisted pair cable, is probably the most common. Then there's shielded twisted pair, coax, fiber, wireless, infrared, like you have for your television remotes, and electronic signals sent through power lines. Now, the choice of networking cabling, or what we call our medium, is rather important because of the extremely high frequency of the signals. Sending 60 cycles utility power through a wire rarely presents a difficulty, but sending 100 million bits per signal or per second signal can be a bit trickier. For this reason, the method of sending signals and the materials they are sent through can be very important. The types of signals that are sent through the network and the speed in which they are sent are extremely important details of a network. All parts of the system must be coordinated together to send, carry, and receive the same types of signals. Now, because networking evolved over several decades, many different cabling solutions have been used. Today, virtually all cables have moved to unshielded twisted pair UTP or fiber optic. Now, and this is all specified in the TIA 568 standards, and because older equipment is sometimes used on new cable plants, adapters called a balance, B-A-L-U-N-S, balance, have become available to make that adaptation. Now, if we're going to look at some network examples, Ethernet being the most popular network type, started on a large coax cable using a bus structure, where each terminal was connected directly to the same physical cable. The Ethernet terminal would then listen to the bus cable, and if it did not see any other terminal transmitting, it could then start transmitting a message on its own. If in turn it sensed a collision from data being transmitted simultaneously from another station, both would stop. They would have to wait a random bit of time and then retransmit. This access is called CSMA-CD, or Carrier Sense Multiple Access with Collision Detection. Now, Ethernet uses unshielded twisted pair wiring and is called 10 base T. 10 being the speed in which it operates, 10 meg. It's a baseband transmission, and the T stands for twisted pair. Now, this wiring scheme connects each Ethernet station to a hub that retransmits to all connected stations, duplicating the function of the original backbone coax with a simpler, less expensive cabling. Now, an alternative network connection is on a ring where all stations are connected to two other stations in the network, forming a ring. Access to the ring is by what we call a token, or a data packet transmitted from one station to the other in sequence. The station with the token can transmit data when it receives permission indicated by the arrival of a token. The first widely used ring network was Token Ring from IBM, but it has been overshadowed by the popularity of the simpler Ethernet and is now virtually obsolete. High-speed token ring, called FDDI, became quite popular as a backbone for large networks. FDDI uses a two-ring connection, one active and one backup, to provide fault tolerance in case of a failure of any part of the network. Fault tolerance is now built into star networks by interconnecting multiple hubs or switches into what we call a mesh network, allowing multiple connections. Instead of hubs or switches, devices called routers are used, which can find multiple paths for communications, creating fault-tolerant redundancy. Whatever type of network architecture is installed, the wiring has become standardized. Ethernet began on a complex, expensive coax cable, and Token Ring was on a twisted pair cable with individually shielded pairs. Now almost all LANs use UTP, the desktop connections, and most large networks use optical fiber for the backbone. Using the fiber to the desktop is also becoming cost effective for high-speed networks, or where users do not want to have to continually upgrade a copper UPT network each time a network speed increases. UTP cable has been developed to support most networks up to a gig, or a billion bits per second. The cable has very tightly controlled physical characteristics, especially the twist of the wire pairs and characteristics of the insulation on the wire that control the characteristics of the cable at high frequencies. Normally, wire pair cables cannot carry high bandwidth signals fast enough for LAN communications. The wires also radiate like antennas, so they interfere with other electronic devices. However, several developments allow for the use of simple wires for high-speed signals. The first development is using twisted pair cables. The two conductors are tightly twisted, 1 to 3 twists per inch, to couple the signals into the pair of wires. Each pair of wires is twisted at different rate to minimize what we call cross-coupling. Then, balanced transmission is used to minimize electromagnetic emissions. Now, balanced transmission works by sending equal but opposite signals down each wire. The receiving end looks at each wire and sees a signal of twice the amplitude carried by either wire. Although each wire radiates energy because of the signal being transmitted, the wires carry opposite signals, so the two wires cancel out the radiated signals and reduce interference. Using these techniques and having two pair of wires sending signals in opposite directions, it has been possible to adapt UTP cables to work with Ethernet and token ring networks. At higher speeds, signals are compressed and encoded, and multiple pairs are used for transmission in each direction to allow operation with networks of over 1,000 meg per second. UTP has 4 twisted pairs in the cable, 2 of which are used to simultaneously transmit signals in opposite directions, creating full duplex links. Some of the higher speed networks now use all 4 pairs to reduce the total bandwidth requirement of any signal pair. Some cables have been offered with a high performance guarantee only on 2 of the 4 pair, but these cables can be troublesome if the cable plant is ever upgraded to high speed networks. Although most networks only use 2 pair of the 4 pair available, it is not recommended to use the other pair for telephone or other LAN connections. However, adapters are available to allow multiple signals to use a single 4 pair cable. UTP limitations on distance and bandwidth have led to the widespread use of optical fiber, generally multi-mode, in LAN backbones. Optical fiber can also be used directly to the connected devices. This requires using hubs and switches with optical ports and media converters at the PC, but allows removing all electronics from the telecom room, often at significant cost savings. Today, all network wiring has migrated to a physical star topology, with all cables going out from a central communication room. This topology is specified by the 568 standards, which you will hear much about later on. Now, these are the basic considerations for network systems. All of the confusing terms associated with networks simply describe things associated with these basics. So in reality, the basic operations of networks are fairly simple. The real problem exists in the methods, and it seems like they all have some new name used to accomplish parts of these basic operations. As we continue through our discussion of networks, don't lose track of the fact that all the other details are merely methods of accomplishing these tasks and nothing more, no matter how terrifying they sound. So in conclusion, remember that telephones use a single pair of wires that connect the phones and a power source, which causes a current to flow in a loop. The current is modulated by the voice signal from the transmitter in one handset and excites the receiver in the opposite handset. They are connected in switched networks and have low bandwidth. A standard video signal uses 6 MHz of bandwidth, is highly coded, and can be modulated, transferred to a different base frequency to be used in many transmission signals or channels. Most cable TV distribution is over a tree and a branch system using a hybrid fiber and coax cabling system. Computers are connected with network interface cards in either twisted pair or fiber optic cables. Computer networks are usually the star type, with every machine connected to a central computer room. And that concludes our lesson for today. Tune in shortly. We'll have chapter 3 up and running for you, and we'll see you then.